Hello everyone, welcome to my part 1 of my lecture 3 on the course Soil Mechanics, and the lecture is about the index properties and the soil classification.
So, in nature, soil occurs in many varieties and types. So, for the ease of a civil engineer, for their convenience to put a very concise and systematic approach in uh, dealing with the soil, the classification of soil is very important. That is, we basically categorize the soil into groups or classes. Each group or class is made based on having similar characteristics and potentially similar behavior that our soil will show. Right? So the relevant criteria which is used for classifying the soil are the consideration of the index properties of the soil. What are these index properties? These are nothing but the various physical and engineering properties with which a soil can be identified. These index properties are broadly classified into two. One is the soil grain property, another is the soil aggregate. So these soil grain properties are all those properties which pertains to the individual solid grains, and they remain unaffected by the state in which a particular soil exists in nature. That is, they are independent of the manner of soil formation. Some of the examples of soil grain properties are the particle size distribution, which is very important, and we learn about this in the next slides. The specific gravity, the grain shape, size, right? Another is the soil aggregate property. The soil aggregate properties are those properties which are dependent on the soil mass as a whole, and therefore these properties control the behavior of the soil in the field, as any civil engineering project is actually founded on the field, right? So these soil aggregate properties represent the collective behavior of the soil and is influenced by the stress history of the soil, the mode of soil formation, the soil structure, right? So these properties are very much important as they represent the true undisturbed natural soil deposits on which the engineering structures are founded on and are designed accordingly, right? So when we are talking about the soil grain properties, let us talk about the shape of the soil grains, right? Which is a useful soil grain property, especially useful in case of coarse grain soil, as it can be visible with the help of naked, whereas in fine grain soil it would require microscopic examination, and definitely, especially for coarse grain soil, it is very important in influencing the engineering behavior of the soil. So when we refer to as the grain, we can say that the soil grain is bulky. So these whatever grain shape classification we are talking about, it's not very universally accepted, but it's very descriptive classification that or qualitative classification that we give. So what we refer when we refer to as bulky soil grains, so here the soil grains, the dimensions are more or less the same in all, right? So it's basically a characteristics of sandy or gravelly type of soil. And initially, like in the geological cycle, when the rocks are withered and eroded, the bulky soil grains are usually angular, but as they are transported, these transportation agencies, the sharp edges of this bulky grains are usually worn out and they become more rounded or sub-rounded, right? So, like for example, we have talked about alluvial type of soil, right? So, alluvial type usually show very subangular or sub-rounded type of grains. Okay. Next, we have flaky type of grains. So, flaky type of grains is the ones where the dimension of the grain in one side, namely like its thickness, is very negligible compared to the other lateral dimensions of the grain, right? So they represent like a sheet of a paper or a leaf of a paper, and they just settle like that of the leaves drifting from a tree. Okay, usually clay type of minerals shows this type grain shape. Clay type of minerals also show grain shape which we call as needle shaped grains. So in the needle shaped grains, one dimension of the grain is fully developed and it's much larger than that of the two. So it resembles like that of a needle, and usually kaolinite type of clay mineral shows these characteristics. So what is this kaolinite mineral? We will talk about later in the lecture series. So these are all about my grain shapes, which is of the soil grain property. So let us talk about another soil grain property, that is specific gravity of the soil solids. So we have already talked about the definition of specific gravity in the previous lectures of this course. So now let us quickly know that how we can determine the specific gravity. So let us talk about another important soil grain property, that is our grain size distribution. Soil consists of different sizes of particles. The amount of a given size of particles in a particular quantity of soil therefore varies from one soil to another. So in order to classify the soil, it is important to determine the percentage of the various sizes of the soil grains present in the given dried soil sample, and that referred to as the grain size distribution. For coarse grained soil, usually the grain size distribution for both coarse grained and fine grained, we do this particle size distribution determination in laboratory by two ways. One, which we called as the dry mechanical analysis or sieve analysis. So we have sieve analysis. Other we have the wet mechanical analysis or hydrometer or pipette analysis. So usually coarse grained soil are the grain size analysis is carried by sieve analysis, whereas for fine grained soil are usually analyzed by the hydrometer method or the pipette method. Well, usually it contains both coarse grained and fine grained constituents. So a combined mechanical analysis needs to be performed, which consists of both the sieve analysis and the hydrometer analysis. So we have talked about sieve analysis, right? Usually the coarse grained soil are subjected to sieve analysis. So what are sieves, right? So basically sieves are like pans, right? So the pans have wire screens which have different square openings. According to the Indian Standard Code of IS 460 1962 revised, the sieve number is basically expressed as the mesh width or the width of the openings, right? So they are expressed in either millimeter for large size sieves or in microns for smaller size sieves. For Indian standards, sieve size may vary from 80 millimeter to 75 micron, right? So usually any soil sample, any representative soil sample is usually passed through these sieves and is separated into two fractions. That is, the one fraction that passes through the 4.75 millimeter sieve and another fraction retained on the 4.75 millimeter sieve. So 4.75 is a considered sieve diameter, where the particles which is retained, we call it as the Will fraction, and the particle which passes through the 4.75 millimeter is basically the fine fraction of soil. So gravel fraction of soil is usually subjected to coarse sieve analysis. So usually a set of sieves are kept for this coarse sieve analysis of 80 millimeter, 20 millimeter, 10 millimeter and 4.75 millimeter sieve. The one which passes through the 4.75 millimeter sieve is subjected to fine sieve analysis, and suppose if sand, we undergo this fine sieve analysis, or if it is such that particles which are smaller than 75 micron sieves are present, like silt and clay, then we undergo sedimentation analysis that will be taught in the subsequent slides. The IS sieves which are used to analyze this fine fraction is usually consist of sieves of sizes 2 millimeter, 1 millimeter, 100 micron, 425 micron, 212 micron, 150 micron, and 75 micron. So the particles which goes through the 75 micron sieve are subjected to sedimentation analysis. So what is the procedure, right? So we take the representative sample of soil, which is well pulverized dry soil of a known weight, and is sieved through a selected set of sieves arranged according to the sizes. So usually the arrangement comprises of sieves, right? So sieves are arranged like this, such that the largest aperture sieve is placed at the top, and as we go down, the size of the sieve decreases. That is, the smallest aperture sieve is at the bottom. Also, a pan or a receiver is kept at the bottom, where the soil is finally retained after passing through the set of sieves, and a lid is placed at the top of the top sieve to retain the particles so that it does not scatter around when the whole arrangement is shaken. So this arrangement is basically using of any mechanical shaker. Try to shake this, and the amount of shaking depends upon the shape and the number of particles. And after that, what we do, we weigh the amount of soil retained on each sieve. So after shaking, we check the different sieves and weigh the different soil, amount of soil retained on each sieve, right? And also we know that what is my total weight of the soil sample taken, right? So what we do some mathematical calculations. We find out the percentage retained on each sieve, which is equal to the weight of soil on a particular sieve divided by the total weight of soil sample taken, right? Now what we do, we find out what is the cumulative percentage retained. That is, we find out the sum of the percentage of soil retained on sieves of larger sizes and the percent retained on that particular sieve. So this will get more clear as we will solve a problem in the subsequent slide. So this is my second step, and finally we find out what is my percentage finer. So the percentage finer is equal to 100% minus cumulative percentage retained. So basically we find out the percentage of the total weight of the soil passing through each sieve. That is my percent finer than the sieve under reference. So in this way we determine, or what we say as a particle size analysis using sieves, and by calculating this percentage finer, and as we know the particle sizes of the soil which corresponds to the sieve sizes, we can draw a graph which is called as the particle size distribution graph that we will talk about little later, and from that we can get an idea of the different percentage of the sizes of the particles that is present in that soil. So in the sieve analysis, the finest sieve size that we use is 75 micron or 0.075 millimeter, right? So if the soil portion passes the 75 micron sieve, we carry out the hydrometer or the pipette analysis, that we also say as the wet mechanical analysis, and this analysis is based on the Stokes law, and it's also the sedimentation analysis. So according to the Stokes law, the velocities of a free fall of a spherical fine particles through a liquid will be different for size particles. So usually if we assume that our soil comprises of grains have the same specific gravity and are of spherical shape, and when they are to fall freely through a liquid of infinite extent, initially the velocity of it will first increase rapidly under the action of gravity, but soon a constant velocity will be reached within a short time, and what we refer to as the terminal velocity. So according to the Stokes law, this terminal velocity is given by unit weight of the soil grains minus the unit weight of the liquid. Here basically the water is the medium of suspension, so we write the unit weight of divided by 18 into eta. So eta here is my viscosity of the liquid, and into d square, where d is the diameter of the grain. So from the relation we can see that larger the soil grain means it will settle faster in water, right? So this fact is used in the hydrometer analysis or pipette analysis to obtain the grain size distribution of fine grain soil. Suppose we consider a jar which comprises of soil suspension. So this is my jar which has my soil suspension, and this is suppose at time t is equal to 0. We will see that as time progresses, the particles of the soil suspension gradually settle down, right? So some particles of the soil suspension starts settling down. So as we see the Stokes' law that my velocity is directly proportional to the square of the diameter of particles, right? That means as time progresses at a certain depth and certain time, the soil suspension will have concentration of different size particles. So if we measure the specific gravity of the soil suspension, we will see that the lower layers will have higher specific gravity, while the upper layers will have less specific gravity. So using a hydrometer, if we measure the specific gravity of the soil suspension at a known depth at a particular time, it will help us to determine the grain size distribution. Usually what happens, we see that as time is equal to T1, my hydrometer is suppose immersed, right? Let us write the depth of the center of the bulb of the hydrometer to the surface of the water or the surface of the soil suspension be Z1. Now basically a equilibrium of force is happening on the hydrometer, right? So what is the equilibrium of force happening? The weight of the hydrometer is acting downwards and a buoyant force is acting upwards due to the soil suspension. So what happens? The weight of the hydrometer remains constant, right? But as more and more particles settle, the suspension provides lesser buoyant force, right? So this buoyant force starts decreasing. So what happens? As time progresses, the hydrometer starts settling or sinking more and more towards the soil sample, means more and more downwards. So suppose at time T2, now the distance or the depth from the surface of the soil suspension to the center of the bulb becomes Z2. So what is to be done is that we have to determine a depth where hydrometer is taking the reading, right? So basically we determine an effective depth HE, which is the distance from the surface of the soil suspension to the level at which the density is being measured, basically at the center of the bulb of the hydrometer. So to determine this effective depth, we basically calibrate the hydrometer, or what we say, we have to determine a relationship between the effective depth and hydrometer reading, which we represent it as RH. So basically if we see an hydrometer, it comprises of a stem and basically a bulb like this, and stem of the hydrometer is graduated corresponding to the different specific gravity of the soil suspension. Like suppose it's 0.985, 0.990, 0.995, it's 1.005, 1.010. So like this, the stem of the hydrometer is graduated. In this case, what we refer to as the RH is the hydrometer reading. What we do, that's we notice the hydrometer reading giving the specific gravity of the soil suspension at the center of the bulb is suppose 1.010. So suppose it is 1.010. So what we do basically, we take 1.010, we subtract it by unity or 1 and then multiply it by 1000, and this gives my hydrometer reading, what we represent it as RH, right? So it's basically the reading is here 10, right?
So before we determine the effective depth, first let us find out what is my volume of the hydrometer. So determine, suppose it is represented by VH. So to measure the volume of the hydrometer, we must keep in mind that here we neglect the volume of the stem of the hydrometer and we only consider what is the volume of the bulb. So for this, what we do, we take a graduated cylinder and partially fill with water. After partially filling with water, we immerse the hydrometer into it. Due to the immersion of the hydrometer, we find out that the water level rises in the cylinder, right? So we determine the volume rise, right? So this volume rise is considered to be the volume of the hydrometer.
So now to determine the effective depth, what we do, so let us first take a jar which is filled with a liquid. Okay, this liquid, suppose we want to find out the specific gravity at a depth of the depth which we consider, suppose A dash. The depth of this layer surface of the liquid is what we say is our effective depth, HE. Now what we do, we immerse our hydrometer inside this jar, right? Now due to this immersion, what happens, the AA dash rises to a new height. Suppose we represent it as BB dash, and also the water level, suppose the surface of the liquid, the top surface, suppose designated as CC dash, rises to a new height of D dash, right? So now let us consider the cross-sectional area of the jar BAJ. So this is my cross-sectional area of the jar. So now we see that as the water level has risen from AA dash to BB dash, only half of the volume of the hydrometer is responsible for it, right? So we consider here only half of the volume of the hydrometer. Okay, so what we can write? The height to which the water has risen is VH by 2 divided by the cross section of the jar, right? Now if we consider that our water level has risen from C dash to D dash, we find out that this is due to the whole volume of the hydrometer, or basically as we are considering only the volume of the hydrometer bulb involved in this rise, right? So we consider here the whole volume, that is VH of the hydrometer, and therefore the water risen is VH by AJ, that is the area of cross section jar, right? Now suppose my depth from D dash to the neck of the bulb is H1, right? Or basically this is the point where the RH is taken, that is H1 is the distance between any hydrometer reading RH of the hydrometer, and the total diameter, total height of the bulb is suppose in small h. Now we can write that our effective depth H is equal to H1 plus H by 2 plus VH by 2AJ minus VH by AJ. We can also write after station, that is HE is equal to H1 plus half small h minus VH by AJ. So for a particular hydrometer, if the volume of the hydrometer bulb, the values of the effective depth HE can be obtained for different values of hydrometer reading RH. So a graph can be plotted between HE and RH, which we refer to as the calibration plot, and this calibration plot will therefore take care of the effect of immersion of the hydrometer. When we are talking about the hydrometer reading RH, we must also keep in mind about few corrections that we need to apply to the hydrometer reading, right? So we know that while we were preparing the soil suspension by mixing the soil with distilled water, we have also added some quantity of dispersing agent in it, which will prevent the conglomeration of the particles and prevent the formation of flock, right? So the presence of the dispersion agent will affect the specific gravity reading, that is indirectly or directly the RH value. So the correction due to rise in the specific gravity of the suspension on account of addition of a deflocculating agent is termed as the agent correction, which we represent it by CD. So this is my one correction factor to be, or one correction that needs to be applied to the hydrometer reading, called as the dispersing agent correction. So this CD value is always negative, right? Because the addition of the dispersing agent causes a rise in the specific gravity, which is incorrect. So we have to subtract the value, right? Next correction is due to the meniscus. So as we know that the soil suspension is opaque, therefore the hydrometer reading corresponds to the upper level of the meniscus, which shouldn't be the case. The reading should always correspond to the lower meniscus, right? So a correction which we refer to as CM, which we call is a meniscus correction, is added to the hydrometer reading, right? Another correction that we need to consider is due to the temperature effect, that is, we call it CT. It's a correction due to temperature. So usually hydrometers are calibrated at 27 degrees centigrade. So in case the temperature of the soil suspension is other than 27 degrees centigrade, we apply the correction CT, right? So what happens if temperature is above the standard temperature? The correction needs to be added, so that is positive. And if the test temperature is below the standard temperature of 27 degrees centigrade, this is usually subtracted, right? So CT subtracted. So these are my different correction that needs to be considered, that give rise to my corrected hydrometer reading, which we represent it as RC, which is equal to the RH is the observed hydrometer reading plus meniscus correction minus the dispersing agent correction, and accordingly depend upon the test temperature in reference to the standard temperature, we add or subtract our temperature correction, right? So this RU is what is to be used in the calibration graph to obtain the effective depth HE. Okay. So suppose we want to find out or establish a relationship between the corrected hydrometer reading RC and the percent final. So what we suppose we take a particular amount of oven dried soil sample which are finer than 75 micron sieve and 75 micron size, and we mix it in a given volume V of distilled water. So suppose we mix the soil sample volume V of distilled water, right? So this mixture is, or the soil suspension is thoroughly shaken at the start of the sedimentation to ensure the soil particles are uniformly dispersed in the suspension. Now, as time progresses, at a given depth, suppose we consider a depth of HE measured from the top level of the suspension, only those particles remain which have not settled during this time. So suppose we are concerned with a particular size of soil particle, suppose D. So this means all the particles that are smaller than the particle size D will be present at this depth HE, while the particles which are larger than size D would have settled below that depth at the time we are checking the reading. So we see, as the time elapses, the finer the particle size are retained at this depth HE. So if we sample at time intervals, it will give the content of particles of different sizes. Thus, at any time interval t, so at any time interval t, if we consider that MD is the mass per milliliter of all particles smaller than D, which are still in suspension at depth E, then the percent finer than D is equal to my MD divided by my total dry mass of particles put in the suspension divided by the total volume of the distilled water with which the soil suspension has been made originally, right? So this into 100 as it is expressed in percentage. So we have the mass of the solid as MD in 1 milliliter suspension. Therefore, my mass of water will be simply 1 minus MD by specific gravity, right? So my total mass of my 1 milliliter suspension is MD, which is the mass of all the particles smaller than the diameter D, right, plus the mass of the water per milliliter is 1 minus MD by G. Now suppose RC is my corrected hydrometer reading. Therefore, my specific gravity G of the soil suspension can be determined by 1 plus RC by 1000. So this we have already seen how we are getting G and RC in the previous slides. Therefore, we can just equate the two, right? That is, suppose our total mass of 1 milliliter solution is this. Therefore, my total density is equal to the same, right? Since the volume is 1 milliliter, so it's 1 minus md by g plus md. Therefore, my gravity is equal to the density of the solids by density of water. So water, it's here we are considering 1 gram per cc, right? So simply we can equate G, that is 1 plus RC by 1000, is equal 1 minus md by g plus md, right? So now if we find out that what is md, that is make m subject of formula, we can simply get md is equal to RC by 1000 equal to G by G minus 1, right? So therefore my percentage finer than that of the particle size d we have already written. Suppose we express it as n, like md divided by md by v 100. So md we have already find out and we replace it here as RC by 1000, G by G minus 1, md, that is m small d, is the total dry mass of the which are put into suspension, and we keep it as it is. Now divided by V, V is the volume of the distilled water with which the soil suspension has been made, and suppose we take it as 1000 milliliter, so we just simply put 1000 milliliter, and the percentage finer is expressed in percentage, so into 100. Therefore we can write N it's equal to 100 G RC divided by MD into G1. So this is the percentage finer with respect to the total dry mass of all the particles put in suspension, that is MD. So here we are also talking about the diameter of the particle, right? We are considering that the particular size particle of d dimension. How to find out d? This can be simply done using the Stokes law, as we can remember from the previous slide. So we have given the equation of a terminal velocity is equal to unit weight of solids minus unit weight of water divided by 18 eta into square. Therefore simply making d the subject of the formula is equal to root over 18 eta into v divided by gamma s minus gamma w. So if the soil particle of the diameter d, we are concerned falling through an height of he in time t, right? So we can find out the velocity. So the velocity is equal to HE by T, right? So we simply replace in this relationship of the D with the viscosity and velocity and unit weight of solids and unit weight of water. So D is equal to root over 18 eta into HE divided by gamma minus gamma W into time T. So we should always keep in mind whenever we are using these equations is the unit of the different terms involved, right? So in this, what we can do for different diameter of particles, we can plot or we can determine the percent finer than that of the particle size d, and accordingly plot a grain size distribution curve, that is having the n or the percent finer in the y-axis and the diameter d in the x-axis. So this grain size distribution curve is usually drawn collectively when we do the combined analysis. Like we also consider the coarse grain soil that have been retained on the 75 micron sieve. So we also take the percent finer of those particles and the diameters corresponding to it, and also we determine the particles size distribution of this fine grain soil, and accordingly we plot it together, right? So we will talk about this grain size distribution curves in more details in our part 2 of this lecture. So thank you for today.